Right, in this video, we're gonna go and learn about enzymes. And what an enzyme is, it's a biomolecular catalyst. And they are very similar to the catalysts you learned about in organic chemistry with a few minor differences. Uh, and those are the differences we have listed here. So they're much, much, much faster than catalysts you use in organic chemistry. Um, 10 to the 6 times 10 to the 12. You're talking about a million to like 100 trillion times faster. And they also work in mild conditions. They have to work inside the cell for the most part. So lower temperatures, 1 atmosphere, neutral pHs, while most chemical catalysts you use in other applications, you'll need quite hazardous conditions for those reactions to happen. These enzymes have very specific reaction specificity, which means you're not going to have side reactions all that much. And usually you're only going to take in one type of product and make one type of, or sorry, you're going to make in one type of substrate and produce one type of product. And these enzymes are regulated. This is especially important for metabolism, but any other type of enzyme, you need to be able to turn it on, turn it off, speed it up, slow it down. And so we're going to look at the types of regulation as well. On the bottom here, I just have some reactions just to give you, how much faster they are. So carbonic anhydrase is going to be our fastest, one of our fastest enzymatic rate reactions here, and it speeds it up versus a non-enzymatic rate by 7.7 million times. Staph nuclease is one of the fastest rate enhancements we see when we compare the non-enzymatic rate to the enzymatic rate. So the enzyme takes 95 reactions per second, basically, is what this unit means. Here, for this reaction to happen, you're looking at, years maybe for it to happen without an enzyme. So our rate enhancement is times 10 to the 14th, a very massive number. And when we talk about enzymes, you have 6 general classes of enzymes, which are shown here. But if you ever come across a molecule and it ends in the word ace, that's kind of your hint that you're working with an enzyme. So urase and alcohol dehydrogenase. A lot of the times these enzymes are named after the reaction they do. So urase works with urea. Alcohol dehydrogenase works with alcohol. That's not always the case, though. You'll find some enzymes called like catalase and just have names that don't have anything to do with their reaction. Enzymes, newer enzymes that are discovered usually have much better names than old enzymes that were discovered in the 50s and such. And when you find a new enzyme, there's a systematic way to number it, similar to IUPAC for naming organic chemicals. Here we have a numbering system for enzymes, where they have a class, a subclass, and a subclass. So here we have like EC 4.2.1.3. So these classifications are really useful. So this tells us this is a lyase of class 2, subclass 1, class 3. Don't need to worry about that too much. Like I'm never going to ask you to know these numbers, but just be aware if you ever look up an enzyme on the internet or you're working with an enzyme, the numbers are just a classification scheme. That's all it is. So our first question here is, why do we need enzymes? Well, hopefully the first slide got that across. Without enzymes, we could not do reactions on the scale or on the speed we would need to have life. And so we would all die because reactions would be much too slow. Now, let's look at the ways we think of enzymes working on a specific substrate. And there's two types of models that we have. We have the induced fit model, and we have the lock and key model. Now, the induced fit model is your substrate binds very weakly at first, and when your substrate binds weakly, the uh, the site where you're binding undergoes a constant conformational change. And that conformational change makes your substrate and enzyme bind more tightly, and your reaction can go forward. Another way people think about enzymes and substrate is the lock and key model, where your substrate and your enzyme form a perfect, uh, uh, already a perfect fit, like a lock and a key. Um, so far, what people have determined is that the induced fit model is probably the one that is more likely to happen. Um, but the lock and key model is still useful to think about for certain applications. Now, I did say that, one of the advantages that enzymes have over catalysts is that they're specific and hardly have side reactions. But some enzymes are more permissive in what they will use as a substrate. For example, alcohol dehydrogenase, what that usually does is take ethanol and make it to acetaldehyde, um, while methanol, which is one carbon different than ethanol, will make it into formaldehyde, which is deadly. So that's why if you drink ethanol, you're just going to get drunk. If you drink methanol, you're going to go blind because it makes it into a chemical that's deadly for us. Alcohol dehydrogenase can also work on isopropanol and make it to acetone. So acetone is more or less nail polish remover. That's the main substance there. So you'll have very sweet smelling breath, for example. So most enzymes will work on molecules that are similar to the substrate it is designed to work on, which is good when it comes to, we want to block this enzyme, inhibit it, which we'll get to later on in the class. So question 2 is a review question, so make sure that you can answer this. So cofactors, what's a cofactor? A cofactor is another molecule some enzymes may need to work. Not all enzymes need cofactors. That's why I have like chemical teeth, right? So if your enzyme's your mouth, right, the jaw is doing a lot of the work by moving up and down, but you need your teeth there to actually break apart the food. So it's a system that works together where the jaw would be your enzyme and your teeth are the cofactor here. And there's two types of cofactors. You have your coenzymes and metals, right? So a lot of enzymes, especially those with DNA, will just have a metal ion as a cofactor. But if it's an organic molecule, we call that a coenzyme. And we have two types of coenzymes, the co-substrate and the prosthetic group. So the difference is, are you attached permanently or are you not? So when we talked about hemoglobin, heme was always attached to hemoglobin, right? Never came off. It was covalently bound. So that's a prosthetic group. While a co-substrate is something that binds and then unbinds, just like the substrate, right? The substrate has to bind for the chemistry to happen. So the co-substrate also has to bind. And talking about enzymes, we have some different vocabulary here. We have the holoenzyme, which is everything together, right? The complete unit with cofactors called the holoenzyme, while the apoenzyme is if you remove the cofactor and it's just the enzyme portion, that's called the apoenzyme. And during a reaction, usually the cofactor is changed during the reaction. Not always, like metal ions don't always have to be changed. But if the cofactor is changed, you have to regenerate it for this reaction to continue. Um, so that's a common theme when we look at mechanisms, right? To do a reaction, you have to always have your enzyme return to the original state, or your catalyst will be dead after one reaction. You don't want that to happen. All right, so let's get into some diagrams of the enzymatic process, right? So let's focus on the bottom left here. I'm going to start labeling things. So on the left hand, well, on the x-axis, let's just start labeling that. On the x-axis, we have reaction coordinates. The way to think about that is the start of the reaction and the end of the reaction. So at the start, we have our reactants. In the end, we have our products. And free energy is on the y. And at this hill, we have what's called a transition state, which is the highest energy form, right? So let's look at the reaction we're actually doing here. We have molecule HA being bound to molecule HB. And we also have molecule HC not bound. That's our reactants. Our products is B being bound to C, but A is now free. So our transition is where we have the bond being like half formed, half broken between A and B, and half formed, half broken between B and C. So we're breaking one, forming the other. The transition state is when we're like halfway there. Right. So any transition state is just a hill. It takes a lot of energy. So one thing we need to talk about is the energy from the reactants to the top of the hill. That is called delta G double dagger, or the free energy of activation. And the bigger this number is, the slower your reaction, because the rate of a reaction is equal to the exponent. Remember, E is exponent. So it's the exponent of this. Negative delta G divided by RT. R is the gas constant, T is the temperature. So the higher the transition state is, the slower your reaction, because the greater delta G double dagger is. Right. So that's one thing on this graph. The other thing on this graph is delta G reaction. And that is the energy difference between the reactants and the products. If the products are lower in energy than the reactants, overall delta G is negative. That would be termed a spontaneous reaction. If delta G is positive, that would mean our products are higher than our reactants. That's non-spontaneous. A thing to note though, energy and kinetics are not related. Kinetics, how fast this reaction is simply based on delta G double dagger. So I could have a reaction like this, where it would technically be spontaneous because delta G is negative. However, delta G double dagger is so high that this reaction on its own would probably never happen, or it would take a very long time, right? So keep that in mind. Kinetics and thermodynamics are separate fields. They are not related to each other. Just because something is spontaneous does not mean it will happen quickly. It could be incredibly slow. So what does an enzyme do then? The way an enzyme speeds up a reaction, which is shown in this blue image, is that it lowers the transition state energy, right? So here we're lowering delta G double dagger. So in blue, this is delta G double dagger. For our catalyzed in red, it's right here. So we are lowering this energy, which speeds it up because of our equation that we set. A thing to note, overall, the free energy of the reaction doesn't change. Delta G of the reactants and delta G of the products do not change. So a enzyme or a catalyst does not change the thermodynamics of a reaction. It only changes the kinetics. So some terminology here. The difference in free energy between the catalyzed and uncatalyzed reaction, we call that delta G, delta G double dagger, or delta G double dagger cat. The way to read this, it's a really weird symbol, is it's the difference in the difference of delta G double dagger, right? In the uncatalyzed version, that was just delta G double dagger. So what we're saying is, well, what's the difference in delta G double dagger if you have a catalyst? That is this energy. You just subtract the two and you get delta G double dagger. And with that, we can see how much faster the reaction happens, because that is exponent delta G double dagger divided by RT. So that is how a reaction speeds up. We just lower the activation barrier. And since reactions can be reversible, a catalyst actually speeds up both directions. So that's what the right plot's saying. Let's take a look at the left plot. Here at the left plot, you can see we have two activation energies. And we have this valley. Anytime you have a valley like this, that's when you have an intermediate. Right? You will have a buildup of a stable substance that's not a substrate and it's not a product yet. That's your intermediate. That only happens when you have a valley like this in your energy diagram. And since we have two transition states, whatever is highest is your rate limiting step. That is, whatever hill is the highest determines how fast your reaction goes. So here in blue, the first hill is higher than the second hill. So in blue, first step is rate limiting. In red, the second hill is highest. So in red, the second step is rate limiting, right? So whatever has a higher delta G double dagger will be your rate limiting step if you have a reaction that has multiple transition states. Now, I have a bunch of questions. That's all the rest of this PowerPoint. So I'll leave that up to you to do. So you spend the rest of the time that we would normally talk about this stuff and go over this. See if you can answer them. Let me know if you have questions. I'll put up the answer key for this. But yeah, that's all the material I have for today. So I'll put up a homework that'll be due next week, Friday. And I'll be back live in person on Monday. So I hope to see you then. And have a good weekend, everybody.